thank you for being here with us today at our 2021 Beyond Big Data virtual event. If you have questions at any time, please feel free to send a message using the chat feature, and we will address at the end of each session. We are going to jump right into breakout number 1, part 1, MLOps, moving AI ML to production, and I am so pleased to welcome our presenters for this session, Brad Egler and Robin Stringer, who are both customer engineers at Google. Brad and Robin, thanks for being here this morning on our final day of Beyond Big Data for 2021. The virtual stage is all yours.
All right, thank you very much, Allison. Good morning, everyone. Thanks for taking the time to join our breakout session today. We're going to talk to you a little bit about ML operations. So my name is Brad Egler. I'm a customer engineer at Google. I've been with Google for about 1.5 years at this point, focused mainly on data analytics and machine learning, generally looking at that through the lens of application development. Before that, I worked at a smaller cloud provider, but I've spent most of my technical career in the development side of the house, doing engineering and architecture work for Fortune 10 organizations. I'm joined today by my partner, Mr. Robin Stringer. Robin, you want to introduce yourself?
Hey, morning everyone, and thanks for joining. I'm Robin Stringer. I work alongside Brad at the Pittsburgh office of Google. I've been at Google Cloud for almost a year. I've been fortunate to work with several companies that are interested in applying AI to hit their moonshots in different arenas. Previously, I worked as a machine learning engineer at a large consultancy and worked on end-to-end applications at companies around the United States.
Yeah, so as we said, we're based out of the Pittsburgh office. If you've been keeping track of Google in the Pittsburgh area over the last few years, we've grown significantly. I think when I started, the cloud division was maybe a handful of people, and we're probably approaching that 50 person watermark at this point. Large investments coming into the city in the next year as we expand even further, taking over additional floors at Bakery Square. So there's always room for new Googlers. If you're interested, come check us out at some point. It's a great time to be in cloud and a great time to be at Google. So as I said, we'll talk for a few minutes, 15, 20 minutes on MLOps. We're going to start with kind of a definition of what that is. We've built a somewhat fictional case study to talk through kind of the evolution of the different organization as they grow into their like true machine learning as a true machine learning powerhouse. So what exactly is MLOps? So back in 2015 or so, Google researchers coined this term of hidden technical debt. And what they were really talking about was the different components that are necessary to train, deploy, and maintain accurate machine learning models at scale, right? It ranges from things that, wrap your model, such as ingestion, transformation, the different model architectures that you might choose, how you deploy a model, how you monitor that model, what you do to retrain that model with fresh data. And all of these things really have interdependencies and different requirements, right? So in most cases, you've got to think about versioning of these systems and securing them, who has access to what, so forth.
Okay, so as deep learning, machine learning exploded in various applications over the last decade, and particularly the last 5 years or so, the machine learning code was just all powerful. It was this magic kernel that people wanted to get their heads around. And I remember when having a working convolutional neural network that recognized images was seen as this enormous victory and such a cool thing to have. Then everyone started thinking, well, hang on a minute, what do we actually do with this? How do we deploy it? How do we get it to our users? And what if we have 1 million users? What do we do then? How do we retrain it? How do we improve it? And so now, as Brad was saying, the machine learning code is a fairly small part of a huge application. So it comprises now things from data collection, data management, to analysis tools, logging facilities, automating all this, and then serving batch and online predictions. So, excuse me. So to bear in mind that just how machine learning code forms a crucial and yet small part of a mature machine learning application.
So taking a step backwards, I'm sure most of you are aware of DevOps and the DevOps movement, how the industry has changed over the last years. But for those that haven't, right, what we're really talking about here is, treating everything as code, right? Your infrastructure is code, your source is code, your environments are treated as code, right? We apply the same practices that we would have applied in development for engineering work to the operations field of work, right? And we also want to talk about introducing monitoring and observability of those functions as well, and bringing them back into your CI/CD pipeline. Fairly famous study that was done around organizations that adopt DevOps, the Accelerate State of DevOps report. And what they found really is that the elite performing organizations are deploying to production almost 100 times faster than other organizations, right? Their rate of change is astronomical compared to a more traditional company that hasn't adopted these practices. And the interesting byproduct of that is increased stability, right? As you do something repeatedly over and over and over again, you become more proficient at doing it, and your margin for error gets smaller and smaller. Less times, you spend less time dealing with the intricacies of individual environments and more time on just producing quality software and getting it out into the world. So when we talk about MLOps, what we're really saying is let's take all of those DevOps practices that we learned over the past 10 years and apply them to our machine learning workloads. And what this really means is, from a practical standpoint, is taking the code that's there to build your ML model along with all of the inputs to it and treating them also as code and wrapping source control around them. So if you have a series of hyperparameters that you use to tune your model, that becomes part of a metadata store that you now track again. If you ever need to reproduce a model, you'll now know what data set it was associated to, what parameters were used to create that model, how it was built, where it was deployed, when it was built. In the event of some sort of analysis that you have to do in the future where a new model is for some reason underperforming compared to a previous version, or you can go back in time and revisit it.
Okay, so let's introduce our fictional case study. Pittsburgh self-driving bicycles is a young robotics company that wants to use machine learning to create autonomous bikes. This is something I think we can all agree we'd greatly benefit from. They're a year old and they're prototyping self-driving software in simulated environments. They have various ML model needs, which we'll talk about in a second, and we're going to follow them as they march through 3 phases as they mature in practice and product. So a manual phase, a strategic phase, and a fully automated phase.
Just to level set just a little bit, if you've never developed a self-driving bicycle, the things that you may face as challenges really come down to data collection and labeling. Right? Those are the biggest hurdles to getting started. How do I get images of everything that happens in the world? And then how do I put that in front of a person and let them say, okay, that's a car, that's a dog. How do I, build a bicycle that can avoid dogs, right? Dogs love bikes. That's if you've got a bike that's driving itself, how does the bike know to dodge a dog and not get attacked and all of your expensive hardware be destroyed? Taking just a slightly closer look, if you imagine that a bicycle outfitted with a series of cameras and sensors is going to feed an enormous amount of data that has to be captured and stored somewhere. The processing of that data is going to use massive amounts of computing power. And the logistics of putting bicycles on the road with human riders that are attempting to capture this data is complicated. So you're going to want to build the ability to run simulation for tens of thousands of miles executed every day, just so you can tune your models to be as accurate as possible.
So here are some of the models that Brad mentioned. We need to not only detect objects, but track them. Is that car going in a direction away from me, or is it likely to be coming towards me? Same for pedestrians and, of course, dogs. Image classification. So there are so many things to classify in any city snapshot, from road signs to people to bollards. The list could go on for hundreds of items. SSDB is currently on the fence with LiDAR, radar, and ultrasound. They're experimenting solely with cameras. However, in future, they may have to look at ensemble models to put all these technologies together and come up with a coherent view of the world. Okay, changing lanes. So let's talk about the manual phase. They're getting off the ground in the spring, and their data scientists are doing experimentation locally on their laptops. They have just 5 bicycles on the road in one city, and they're producing 3 terabytes of data a day. The data labelers just can't keep up with this volume of data, and 2 laptops have melted. A third's on life support after being asked to train models. Let's have a look at a diagram that shows this manual workflow. So firstly, we have local data stored on-prem on servers, and the data scientists are working to do exploratory data analysis on their laptops. This creates so many problems. They have no ability to share notebooks beyond emailing them back and forth. Version control is very difficult. They quickly lose track of which notebook is current, which is the cutting edge, and whether changes in one notebook were integrated into another before they're sharing them. So there's no version control. The models aren't containerized, so that all those Python import statements that you see at the top of a machine learning model in TensorFlow or PyTorch, those libraries may be out of date next week or cause clashes with other libraries. So they're not using containers to simplify that process. Here's what the experiment steps look like. So they do their feature engineering or data preparation, model training and evaluation, again on their laptops in their local environments. Hyperparameter tuning is done by hand, which means they have to wait around for the models to finish training. Now, cutting edge models on images can take months to train, depending on the hardware you have at your disposal. So data scientists spend an enormous amount of time just waiting around for models to finish training before they check the validation and the test results, tweak hyperparameters like dropout or batch normalization again, retrain the model, and all this is very time consuming and inefficient. Somehow they get to a trained model, which they then store in like a model repository or storage. And then they just hand it over the fence to ops and hope for the best. They just hope that ops knows how to deploy a machine learning model. So here we see this disconnect between machine learning and ops. The ML engineers think their work is done when the model is trained, and the ops crew has to figure out what to do with it. The development and production environments are essentially the same, and there's no monitoring, which means it's difficult to track progress, and there are infrequent releases and updates. Okay, so the Pittsburgh self-driving bikes, their executives take note of some of the data scientists' visualizations, and the CFO is really impressed on a spin around the parking lot in a Polkadot 1 prototype self-driving bicycle. They throw their weight behind the AI development efforts, which allows them to enter the strategic phase. And we're looking 6 months down the line here. So they now have 18 bicycles on the road in 2 different cities. So they're getting varied training data. They're running 20,000 hours a day of simulations virtually. They're producing 300 terabytes of data a day, and their compute hours are growing exponentially. They realize that they can't possibly store all this data on-prem. So they're moving the data to the cloud. And now that they're in the cloud, they're able to scale what they're doing and start looking at automating some of that machine learning loop that we just showed previously. So let's have a look at an architectural diagram for the strategic phase. Firstly, we have a feature store. So this is a step up from just putting everything into a cloud storage bucket. This is a centralized repository for sharing and reusing ML features across use cases. Here we see experimentation starts to be orchestrated into pipelines. So from data extraction to model training and evaluation starts to be put into a format that data scientists can start to use and tweak very, very quickly. So they can run 10 experiments in parallel just by performing small tweaks on the pipeline, rather than having to rewrite everything from scratch or make significant changes every time they want to do something. Running and evaluating 10 models in parallel is much more effective than just doing one after the other. We start to incorporate CI/CD practices. In building the components and pipelines, we start to use containers. So this means that no longer do we have library conflicts, and that it's very, very easy to create small, testable, reusable components. We can run automated tests, tag and store the artifacts, and then deploy them to the target environment. You'll notice at this stage, we're also starting to develop an artifact store, and this is crucial for everything from data lineage to checking for data drift, and tying everything together so that you can see exactly how a model was trained, what the data set, what the state of the data set was in at that point in time, what the hyperparameters were, etc. This allows us to get to what we call continuous training. And continuous training is really, really crucial, especially for self-driving bikes, because you want to avoid two things. The boxes in red show the data validation and model validation steps. So we have to check for data drift. So if you imagine they started collecting data in the spring in Pittsburgh, and then 6 months later, when you're starting to get gray weather and then snow, the data is less and less relevant because the city looks so differently with low light and snowy conditions. This also creates a huge drop in model efficacy. So we need to enable continuous training to make sure that that doesn't happen. And well, everything is stored in a metadata store for reference. Okay, so a year on since that first spring, Sixburg self-driving bicycles enters the fully automated phase. So that's a phase of machine learning maturity where they have a huge number of bicycles on the road now. So more than 300 bicycles across 6 major cities. They're running hundreds of thousands of hours per day of simulations, and they're producing more than a petabyte of data every day. They have a 10x growth in compute hours, and they have fully automated an ingest, label, train, validate, deploy loop. So one more architectural diagram to see what that looks like. Here's our feature store feeding experimentation and development. Via the code repository, we have the training pipeline CI/CD process, an artifact repository enabling continuous training, storing necessary data in the ML metadata and artifact store. We have a model registry, which is pumps the validated models to model serving, and then the serving infrastructure allows us to get into the habit of monitoring everything and making sure that the models are still performing effectively day by day. The crucial last thing here is this arrow taking us from the serving and monitoring back to the beginning experimentation and development. And in reality, you can re-trigger this entire cycle based on a timeline. So you would like it to train every day. You could set it up for event-based retraining. So if you get a data drift or a drop in model accuracy, or you ingest new data, for example. So there's many ways you can set it up to make sure that the pipeline is staying fresh, the data is staying fresh, and the model is maintaining or improving its accuracy. A word on culture. At this point, there's this integration that happens. So the ops, the AI, the products and analytics teams are now fully integrated in this mission. And because a lot of the toil that the machine learning engineers had to do previously is relieved, they can now start to help diffuse their complex knowledge to other teams. The data sets that are now stored securely are accessible to all teams for people to come up with more use cases and experiment with new prototypes. The data scientists have the GPUs and TPUs readily available on demand for retraining or to make new workloads. And everyone can now focus on monitoring, maintaining performance, and then thinking about other things that the self-driving bike company would like to do. Okay, so that's a lot of information. I'll now let Brad bring this down to earth with a look at some of the technologies that can make this easy.
Yeah, so if we bring this back to Google Cloud, we've taken all of these things that we've just talked about for any stage of your growth as an organization, and we've built a managed service offering that fully supports your efforts to automate your ML workloads. Right? From data ingestion, things like streaming with Cloud Pub Sub, data management with our enterprise data warehouse, BigQuery, an extensive suite of monitoring tools and automation tools, as well as things, if you're familiar with, processing jobs in Hadoop or Spark, or if you happen to run Apache Beam, we have managed services for those. And we've wrapped all of this inside of our Cloud AI platform, which supports, serverless training, scaling on demand resources to support whatever size workload you have, as well as a model hosting and prediction infrastructure. Now that's what looked like a lot of things, right? But if you really distill it down, what we're talking about is building unified pipelines, right? That integrate with services within our cloud and within other clouds, honestly, where appropriate. Right? And we can build this into a simplified pipeline of model processing and training, and automate the entire end-to-end process. Now, I know what you're thinking. You don't build self-driving bicycles. Nobody in their right mind builds self-driving bicycles. Maybe somebody will someday. But AI and ML really extend to every industry, right? There's opportunity for machine learning to revolutionize businesses all throughout the world, right? From retail to healthcare, financial services, etc.
Okay, we'll leave you with some resources. These detail some videos and MLOps resources. And then at the bottom, if you'd like to experiment with any of these products, there is a free trial on Google Cloud that you can sign up for. Thanks very much for joining us this morning. We'll be very happy to take any questions.
Brad and Robin, thank you so much. We have no questions yet, but I'm going to give people a few seconds to put them in the chat.